All right, that's everybody. All right, let's get started. It's great to have Sandipan Kundu visit us from Johns Hopkins. He told me he was here 2 years ago, and that's why I recognize him, I assume. Here to tell us about holographic CFT and higher spin particles.
Thank you very much for the invitation. It's great to be back here. I've been here, I think, more than 4 or 5 times, I guess. It's great to be back. So this talk is basically in 2 parts. One about holographic CFTs and how they are related to high spin particles. It's not very obvious the connection between holographic CFTs and high spin particles, but I'll explain that in the talk. So this talk is based on these 3 papers. First one from last year with Nima, who is a graduate student at Cornell, Tom Hartman, and Amit, who is also a graduate student at Cornell. And this paper, which appeared in May with Nima and Amit, and another paper that will appear hopefully this month. And I've been saying that for the last 2-3 months, so that so it might be November. Okay, before I proceed, let us remember that it has been more than 20 years of radius CFT. So, and since then, it's an integral part of energy theory. But in last 20 years, other things have happened. For example, this is also 10 years of the new conformal bootstrap program. And conformal bootstrap has significantly changed the way we think about radius CFT correspondence. At least to me, the definition of radius CFT that comes from conformal bootstrap is the most satisfying one. So actually, conformal bootstrap is not that new. The idea appeared in 1973 paper by Ferrara, Grillo, and Gatto, and also a 74 paper by Polyakov. So basically, they introduced this idea of conformal bootstrap, and they used that for 2D CFTs. And actually, they derived a lot of very interesting results for 2D CFTs. But since then, nobody did much with this idea, mainly because it was too simple. So there was a belief for a long time that that conformal bootstrap approach is too simple for high dimensional CFTs. So nobody actually tried anything after these 2 papers. Until this paper in 2008 by Ratazzi, Richkov, Tony, and Vichy. They basically used the exact same idea but for high dimensional CFTs. And they derived a lot of interesting results. For example, bounds on 3D-izing, things like that. So let me give you a very brief review of what conformal bootstrap is. So when we will talk about CFT data, that's basically the combination of dimension of all the operators and the OP coefficients. And the goal of conformal bootstrap is to solve for this CFT data. Obviously, this is a very complicated problem, and in general, one should expect to just solve for this CFT data from anything. So generally, the way it works, somebody will give you some very limited information about the CFT, and from there you will just impose things that a CFT correlator should obey. For example, it should be conformally invariant, unitary, and crossing symmetric. So then you just take generally a 4-point function, you impose all these conditions, and magically sometimes it tells you that only a finite number of, or a subset of all CFTs is consistent with the starting condition that you imposed on the CFT. So among these conditions, crossing symmetry might not be that clear to might not be very clear to everybody. So let me just tell you what crossing symmetry is. So in CFT, what I mean is the following. So if I give you a 4-point function, you can operator product expand. So if I first avoid product expand O1 and O2, then O3 and O4, so I can schematically write something like this. Basically, I'm expanding over all the exchange operators, or I can just choose to operator expand O2 and O3 first, then O1 and O4. That will give me something like this. Now, because it's the same correlator, these two things, they should be the same. So that's crossing symmetry. And this might look like a very trivial expression, but this is actually very powerful when you combine this with conformal invariance and unitarity. Also, I should mention that in conformal field theory, a 4-point function also obeys certain certain analyticity conditions, which are responsible for a CFT. All these analyticity conditions, they are responsible for a causal CFT. I'll explain more. So basically, there is a folklore that analyticity, unitarity, and crossing symmetry, they actually basically gives you causality. It's not an independent constraint. And you can actually, for CFT, actually, you can, for some cases, you can actually show that reflection positivity and conformal invariance actually can give you causality.
Why does nobody ever include this condition in these
Causality?
list? Or either one that's equivalent to it, like
generally, like they just don't write it. They generally use it somewhere in the data, like in the conditions. It's just they just don't say it.
people always give this list, but they never say that part.
For example, they also don't say unitarity, but it's already there. For example, when they write down crossing equation, there are OP coefficients. Whenever you say the OP coefficients are real, that basically that comes from unitarity. For example, if they are imaginary or complex, then all the results that exist, they are not valid. So they are implicitly assuming a lot of things that they don't actually say clearly. Yeah.
So isn't crossing symmetry just a Euclidean analog of causality?
Oh, what? Sorry?
Of crossing, no, not like just crossing symmetry is not. So
Because
if,
crossing symmetry tells you that operators commuted
but
space-like separation.
in Euclidean signature, everything commutes. So
Yeah, that's why I'm saying.
yeah, but causality is a statement about the commutator in the Lorentzian signature. So two operators, like, so crossing symmetry basically tells you that if all your operators are space-like separated in the Lorentzian signature, it's causal. But that's a very trivial statement. So it might happen that in a 4-point function, two of the operators are time-like separated and the other two are space-like separated. Even in that scenario, the correlator should be causal. I mean, and that's the one that actually gives you non-trivial results. The one that trivially satisfied by Euclidean commutation, that actually doesn't give you anything. So the fact about causality is basically if you take the crossing and if you impose reflection positivity, then causality is implied in the Lorentzian signature. So you also need reflection positivity. So in reflection positivity, okay, causality is the statement about, if you take a Lorentzian correlator, causality is a statement about the correlator on the second sheet, not the first sheet result. The second sheet result basically knows about causality. The first sheet result is fixed by Euclidean invariance.
So these are basically standard theorems about equivalence of axioms in like Euclidean and Lorentzian.
Yeah. So it's basically a CFT version of that, yes. But there is nothing new. This is the standard thing. And in last 10 years or so, a lot has been learned from conformal bootstrap. For example, you can just put all this condition in a computer and you can just solve for CFT data. That's numerical bootstrap, and generally it's done in the Euclidean signature. There are many more papers, but I am just showing you first few. But I find the analytic bootstrap more interesting because you are basically deriving facts about generic CFTs by assuming almost nothing. So that's the light cone bootstrap. So this is a very specific limit. Obviously, in general, you shouldn't expect anything interesting to happen. But in this particular limit, where two of the operators are almost null separated, everything actually reorganized in a very nice way, and you can actually use bootstrap to get non-trivial results. And for this light cone bootstrap, obviously, because they are almost light-like separated, obviously it's in Lorentzian signature, but even then, everything is space-like separated. We found that if you take light cone bootstrap, but when some of the operators are time-like separated, you can actually get a lot of interesting results, and they are even more general. In the sense, you can derive facts like average null energy condition just from causality. Conformal bootstrap has also provided us tools to explore how gravity emerges from CFT. I'll mainly focus on that in this talk. So what do I mean by holographic CFTs? If a CFT has a dual description in terms of Einstein gravity or something which at low energies gives you Einstein gravity, it should have a couple of properties. Before I proceed, let me first talk about a scalar operator in any CFT. So if I have a scalar operator in any CFT, the two-point function is fixed by conformal invariance up to some coefficient C0, which can be arbitrary, but again you can just scale phi such that this is just 1. But for scalar operator, because of word identity, phi t 3-point function, where t is the stress tensor, it is completely fixed by the 2-point function. So the OP coefficient for this 3-point function is completely determined by this C0. That means basically, if you tell me the 2-point function, I know the 2-point function. 3-point function doesn't have any new information. Obviously, for operators with spin, that's not true, because for operators with spin, there are more than one OP coefficients. So because of that, like this, the 2-point function is the 3-point function is not fixed by the 2-point function. But for holographic CFTs, this expression, this should be true for operators with spin as well. Let me explain why. Or let me first tell you what I mean. So if I have operators with spin, O, T, mu, for holographic CFTs, it should be completely determined by the 2-point function, plus there will be small corrections. And this correction should be suppressed by a gap, which is basically a scale of new fields. That's the requirement for any, if a CFT has holographic dual description, this should be true for that CFT, for any operator O. And this is a consequence of bulk locality. Let me explain why. Let's take this bulk metric where you have Einstein-Hilbert action plus R square and R cube terms. When I say R square and R cube, they are not just the square of the which is scalar, it's basically all the 4 derivative and all the 6 derivative terms. And M is basically the cutoff scale. I'm in 5 dimension, but that's not important. This is true for any dimension. Let me also add a term for a Maxwell field. I have the regular Maxwell action plus another higher derivative correction where this is wild Maxwell. Again, this should be suppressed by some the same scale M with some coefficient C4. So C2, C3, C4, they are dimensionless coefficients. Now, if you want this to be a causal theory in the bulk, that requires M to be the scale of new physics, as I said earlier, and these C's, they cannot be too large. In the sense, this C, they cannot compete with this M curve. So you are not allowed to tune this C, either C2, C3 and C4 to be so large that this becomes relevant at low energies. So basically what I'm saying is the following.
Is this usually what's meant by locality when people talk about locality?
Yeah,
In
this is it.
holographic. Is it as simple as this, what they mean, or is it simplified version?
So this is a simplified version. So this is basically this is causality, but there might be more conditions.
No, I'm talking about locality, bulk locality.
Yeah. So this is necessary but not sufficient.
Okay.
But in which form is it? It's locality. How do you define locality?
It's basically if they are large, you can have time advances. So this is basically this is local in the sense of asymptotic causality. This doesn't violate asymptotic causality.
Yeah, but it's not obviously related to something like 1 over box explicitly in the action.
1 over what?
Let's say 1 over Laplacian in the action.
No, not like that. No. So this is a weaker version of that. Yeah. So this is basically when I say bulk locality, I mean like this theory doesn't allow to have asymptotic causality violation. So this is a very this is weaker than that.
If C is large, aren't you just basically saying that R squared is not smaller than R? And then
Not really because M Planck is overall. So basically, just if you just make sure that R square term is not competing with R. So if you just rescale everything, you'll see another M Planck will appear here. So that cutoff will be some combination of M and M Planck, not just M.
So this is not saying that derivative expansion is uncontrolled.
Yeah, it's more than that. So if you just talk about when the perturbation series is well behaved, you'll get a defined bound. You'll get a cutoff should be something like, I don't remember for 5D, it's something like square root of M times M Planck, something like that. So basically what this means is the following. So the the leading contribution to the action is always two derivative. So because of that, if I take this theory and find out the boundary 3-point functions, obviously they will always be given, the leading contribution will always be given by the two derivative action. So the two derivative action gives you both the 3-point function OOT and also the 2-point function. So basically that means 2-point function, 3-point function, they are fixed. So this is not something new. This is a consequence of the fact that the bulk action is two derivative. And so the cutoff M that I wrote down in the bulk theory, that corresponds to some gap in the CFT, which is basically related by M times R radius. But this poses a question in the CFT. So why in some class of CFTs, all 3-point function must be tuned to this particular form? Or first I can ask what kind of CFTs you see this particular behavior and why? Why those CFTs have this particular property? Okay, so that brings to the goal of this talk. First, I'll try to address these questions: how gravity-like behavior emerges, or by gravity I mean I always mean Einstein gravity. How gravity-like behavior emerges from CFT. What kind of CFTs have holographic dual restriction? What makes this CFT is holographic? And apparently it doesn't have anything to do with higher spin particles, but I'll explain why they are related. And I'll ask the question, what can we learn about massive higher spin particles from first three questions? And then at the end I'll discuss implications for the cosmology. And this is the outline of the talk.
Sorry.
Yeah.
So your discussion about the 3-point correlators on the CFT side, that they should have like some special form. Does it mean like on the bulk side that your coupling should start like from a minimal coupling? Like
Yeah, but that's not the I'm asking a question from the bootstrap perspective. If let's say I didn't know anything about area CFT, I just want to get a CFT where this is the property of the 3-point functions. So my question is, what kind of what should be the conditions on that CFT? So or basically, if you give me these 3-point functions, I want to find out that particular CFT. And there is an answer. That's why, and actually that answer is not that new. It has been known for at least 6-7 years, I think. So let me go to that. I guess that. So this is first conjecture by Hinskar, Penrose, Polchinski, and Sully in 2009. They conjectured that this the set of safeties which obey two conditions, they have holographic dual description in d greater than 2. First is if you write down the TT two-point function, again that's fixed by conformal invariance. There is some tensor structure over this scaling factor with some coefficient CT, which is the central charge. So that central charge should be very large. So this is equivalent to the large n condition that people talk about in ADS CFT. So this is equivalent to the large n condition. The second statement is the following. The lightest single phase primary operator with spin greater than 2, that should have dimension delta which is very large. So that defines a gap. So in this particular paper, they conjecture any CFT which obeys this two condition, they will have a holographic dual description, irrespective of the microscopic details. The reason they conjectured that, in that paper they actually showed something really incredible. They started with a very simple model for holography. So they have a scalar field in ADS, but that theory didn't have dynamical graviton. So it's basically just a QFT in Cartesian space-time, and they showed the following. So they solved crossing equation as an expansion of 1 over CT, and they showed the number of solutions in that order. There is a one-to-one correspondence between that and the number of different scalar effective field theories that you can write down in ADS. So that implied, or from that they conjectured that probably this set of CFTs, this is sufficient to show that they have holographic dual description. And this is from 2009. And after that, a lot of other papers appeared, and they basically verified the same statement for various different occasions where you have scalar operators as well as some let's say more than one scalar operator or some variation of that. But the conjecture has been completely proven at the linearized level very recently. So it was shown that this conjecture is true even for spinning operator including stress tensor, but only up to 3-point function. For higher point function, it's not known what's going to happen. So basically, what was shown in this set of papers is the following. So in this class of safeties, the 3-point function basically behave as if they are coming from a two-derivative bulk action. And we use causality of the boundary safety, and there are other papers where they use unitarity of the boundary safety, but we ended up with the same final result. So let me briefly sketch how all the arguments go. Generally, they start with some 4-point function in the Reggie limit, where these operators are low spin operator. They can be stress tensor or spin on conserved current or scalars. Then they use conformal Reggie theory to compute this correlator exactly for in some perturbative series. So you know this delta G. Then from unitarity or causality you get constraint on this delta G, and that basically that constraint, if you write down in terms of 3-point function, you get this kind of result. It's basically exactly consistent with what you expect to get from two-derivative bulk action. But this is not very satisfying for various reasons. First of all, all these computations, they involve conformal Reggie theory, which is very complicated, and all the states are really incredibly long, but the final answers are always very compact. So So in other words, all these derivations, they are not very transparent. If you start from holographic CFTs, you start from a 4-point function. All the individual steps are very complicated. At the end, you always get a two derivative bulk action. It also all these derivations, they don't answer the question what makes these CFTs holographic. It's just an observation that this particular set of CFTs, they behave as if they are dual to a bulk gravity theory. And this causality or unitary bounds, they are very suggestive of something deeper.
Sorry to stop you again.
Yeah. Good.
These CFTs, I thought we were talking about holographic CFTs.
Mhm.
What are these CFTs if you just don't assume holography at all? What's the class that defines?
Oh, that's basically, they have to obey two conditions. First of all, that the central charge is large,
Yeah.
and there is a gap for all primary operators with spin greater than 2.
Ah.
So yeah, so that's like when I say holographic CFT, now I mean basically this. But it's an observation that those CFTs behave this way. So I think it's an important question why these CFTs are holographic. And the second thing is this causality or unitary bounds, they are like, if you go to the details, it looks like there is something deeper. It's not just it's not just that it's an accident that these CFTs behave this particular way. Also there is one more reason why I thought there could be a deeper connection. So that's basically, even for generic CFT, you get causality constraint from light cone bootstrap. And these constraints, they are true for holographic as well as non-holographic CFTs. But we found in our previous paper that this is just a tip of the iceberg. Actual condition is basically the average null condition. So the causality basically dictates that the average null condition should be true in quantum field theory, and because of that, you get this kind of bounds. So we have, this also explains one more question that I had before. So it was observed that causality constraints obtained from conformal bootstrap, they are exactly the same as what you get from conformal collider experiments, or thought experiments, I should say. So in conformal collider thought experiment, this is what you do. You start with a CFT, a generic CFT. You insert an operator at the center with this particular wet packet. This is just to localize the operator at the center, and you place a detector far away from the center, and you basically measure average null energy, expression value of the average null energy operator in this particular state. And because this is a positive operator, this quantity should be positive. And if you do this for different operator insertion, you basically recover all the causality constraints. And the reason it basically is that causality dictates that this operator has to be positive. So this is very similar to what we have for holographic CFTs now. So we have, by studying Ricci correlator, we get these bulk conditions, which makes this, which tells you that these CFTs, their 3-point functions, it looks like they are coming from a 2-derivative bulk action. So probably there is something down here as well, and that's actually correct. And we found that there is another energy condition which is stronger than the null energy condition, which is true for holographic CFTs. And because of this energy condition, these CFTs are holographic. And as I'll explain later, this energy condition has a lot of interesting applications. So what is this energy condition? Any question?
Am I supposed to already know what bulk locality has to do with things like advanced signals at infinity or the null energy condition?
That's it.
Am I supposed to already know what bulk locality has to do with null energy condition or signals arriving early at infinity?
It's basically a consequence of that. So null energy condition is true. FRS null energy condition is true for any CFT. So that means basically it's from the bulk perspective. If you send a signal which doesn't go very deep into the areas, if you study causality property of that signal, it should give you a null energy condition.
But you keep saying causality and average null, but we're talking about bulk locality.
Yeah, but that's for generic CFT. So if you forget about holographic CFTs, even for generic CFTs, there are causality constraints, and that gives you a null energy condition. If it doesn't matter if it has holographic dual or not.
Okay.
So that's a generic statement. So for holographic CFTs, there should be something stronger because like average null energy condition is true for any CFT. It's not limited to holographic CFTs.
Okay.
So that gives you basically holographic null energy condition. This is something which is true only for holographic CFTs. So this.
I'm asking what it has to do with locality in
Okay.
bulk.
Basically, that's something I'll explain. So so let me tell you. Let me give you the average null energy condition. So positivity of this particular operator for holographic CFTs. If you impose that will tell you that all the CFTs they should have 3-point functions which is consistent with a bulk dual.
Sure.
Yeah, that's why you have bulk dual basically.
I see what you mean. Okay. By bulk dual, you mean local Lagrangian bulk dual with the action is an integral over a Lagrangian that's local.
Yeah.
That's
It's
what I'm saying now. Okay.
Yeah. So whenever I say bulk locality, I mean asymptotic theory which is asymptotically causal. So basically,
I'll ask later.
basically you are not because like even all the conditions on bulk interactions. So you don't even have to have a Lagrangian. One condition that you can derive from asymptotic causality is basically the 3-point function of graviton is fixed. So that doesn't mean it has to come from a particular action or not. The 3-point function is fixed.
What does that have to do with not having things like, if you had an action, not having things like 1 over box?
No, when I say asymptotic, when I say bulk locality, I mean asymptotic causality.
Oh, well, that's what the question was. Why
Yeah.
is that the same?
So it's a weaker version of bulk locality. So it's necessary but not sufficient.
Okay.
Yes.
Just same question.
No.
Maybe I don't understand. Isn't locality so is locality not independent of causality?
If you have a non-local theory, it doesn't have to obey causality. So that's right. Causality, like it's necessary but not sufficient. So it's not that like if you don't have asymptotic causality that you'll have a local bulk. That's not true. But you have to obey asymptotic causality.
Local bulk theories are always asymptotic and causal. Is that correct?
Yes. Yeah. But the reverse is not true. So that's why I say it's a very weak version of bulk locality. Okay, so let me move on to holographic null energy condition. So it's basically a generalization of the average null energy condition, where you take the same operator, but now you have to smear it over some imaginary direction. So it's not that like we're conjecturing this has to be positive. We can actually show again by using causality of the CFT that this is a positive operator in some sense. I'll explain what I mean. It's basically if you take causality in the Regge limit, and if your CFTs have a large central charge and a sparse spectrum, you can derive that this is a positive. This expression value is positive for some side, not all sides. I'll explain. And this is important. It has the following properties. So if you take the limit r goes to 0, it gives you average null energy condition. So in this particular limit, this is like this positivity of this operator is true for any CFT. The reason this is stronger than actually way stronger than average analogy condition. If you take this operator, find its expectation value, it gives you some number which should be positive. But this is a function. So basically, positivity of this gives you a positive function. So that's way stronger. That's like in principle that's in principle it's basically at one end of that function you get average analogy condition. On the other end, actually, you get all the interesting bounds that you get for holographic CFTs. Yes.
So is V unfixed? The like from other
V?
Yeah, is the
It's not exact. It's basically V is some like if you V is not entirely unfixed. So whenever you do any kind of experiment like collider experiment, all expression values are always measured far away from the insertions. So basically V controls that. So it's fixed in that sense. Okay, so in general, it's a positive operator only for holographic CFTs, and not just that, and it's positivity. It's positive only in a subspace of the total Hilbert space. So you might say then, why do I care? It looks like very it looks very specific, and the reason it's important is the following: the same Hopkins models in a state that we use for generic conformal colliders. It turned out that this operator is positive in that particular state. So because of that, you can actually design another conformal collider, but now only for holographic CFTs, and that's how you get all the interesting bounds for this particular class of CFTs. So, yes.
sorry.
Yeah. Go ahead.
So this unend condition is the stress energy tensor has an unend condition. Do the derivatives of T also satisfy something like that, or the descendants of?
I don't know of any such condition, but let's see. At least observationally, I think that a statement like that can be true. Like some derivatives of an operator might be positive, but I don't know of any argument which shows that they have to be positive. Any other question?
Is this a proposal in the box, or is there?
No, it's not. You can prove it. I can show the proof, but
No, it's okay. It's okay.
I had that slide but excuse me, but you can prove it. Like there is no assumption. Okay, so this is what you can do with this positivity condition. You again design a collider. You insert some operator to create this Hopkins model in a state. You may have a detector which now measures this HET operator, and now you can choose different operators to create this state, and you can basically derive bounds on the 3-point function between this O and the stress tensor. So that gives you this kind of results. Let me skip the proof. It's not. I don't need that. Okay. Let me give you a summary so far. Causality of CFT correlators in the Reggie limit implies that the average, the holographic null energy operator is a positive operator in a subspace of total Hilbert space for CFTs with large central charge and a sparse spectrum. The HET, when applied to low spin operators, explain why CFTs in this class, irrespective of their microscopic details, admit universal gravity like holographic dual distributions. Now, one may ask, what about the higher spin single trace primary operators? And that leads to the second part of the talk. elementary particles in ADS, they are dual to single trace primary operators in CFT. But as I said earlier, like when I talk about holographic CFTs, I basically mean a theory with a sparse spectrum. That means the lightest single trace primary operator has dimension above some gap, which is large. So basically, this is the spectrum of the higher spin operators. You can only have higher spin single trace primary operators above some gap. Now let me do the following thing. Let me add an extra higher spin operator below the gap, and let me ask the question if this extra operator is consistent with the rest of the conditions of a holographic CFT. Before we do that, there are known constraints on higher spin operators in CFT. For example, Malasena and Zurvedov showed that a finite number of conserved primary operators with spin greater than 2 are ruled out. They showed it for in D equals to 3, and then there was a generation in higher dimension by this group of authors. So this theorem implies massless higher spin particles with spin greater than 2 are ruled out in ADS. Or a finite number of massless high spin particles with spin greater than 2 are ruled out in ADS, which is the analog of the Weinberg-Witten theorem, but in ADS. So far this is in, for generic CFTs. For holographic CFTs, there are additional conditions. For holographic CFTs, one can show very easily from the chaos bound that any high spin single trace primary operator xj, they should have a Z2 symmetry, so that any 3-point function of the form xj oo, where O can be any operator you want, that 3-point function must vanish. Otherwise it will violate the chaos bound. Yes.
What is the Z2 symmetry?
It's basically, by Z2 symmetry, I mean like if X has Z2 symmetry, then this 3-point function is basically, it should be equal to x minus. So that basically one way you can just get rid of any such 3-point functions. But this is not, so this doesn't mean this operator cannot be there. Only thing it means is basically this particular 3-point function must vanish. Or in the gravity language, it means a massive high spin particle cannot decay to 2 identical particles in ADS. But as I said, it does not rule out massive high spin particles in ADS. It's a condition on this 3-point function. However, there is one interaction that no particle can avoid, which is the interaction of this form: high spin particle, graviton, high spin particle. So this is, from equivalence principle, we know that this 3-point function cannot vanish. Yes.
For a massive higher spin particle, what is the Z2 symmetry doing?
All I mean is basically like when you write down any correlation function, that correlation function should be Z2 symmetry. So that operator, if you take it to negative of itself, that should be asymmetry.
Why should that be true for the massive higher spin particles?
Because like otherwise, this is something coming out of CFT. So it's known in that sense from CFT you can derive it. In that space you can perform an iconal experiment where you can do the same. You can find the same result. That basically this decay is not. So basically this decay is not allowed. A massive high spin particle decaying into 2 identical particles, that's not allowed. So a Z2 symmetric will basically do that, but it's not. I probably should say that there is a Z2 symmetry. It's basically this is not allowed. So this is an interaction that should be, if you have a high spin particle, this interaction should be non-zero. In the CFT language, that means this 3-point function xj t mu nu, that cannot be 0. Okay, now let's focus on this particular 3-point function. If I have a high spin single trace primary operator in a CFT, again its 2-point function is fixed by conformal invariance up to some coefficient. 3-point function this 3-point function is also fixed by conformal invariance up to 3j independent OP coefficient. So the tensor structures are fixed, but the OP coefficients can be arbitrary. And there is one more condition that comes from what identity. It's basically a particular linear combination of these 3j OP coefficients will be equal to this Cj. Yes.
Are you considering the xj's to be conserved? Or
No. So when xj's are conserved, they correspond to massless particles in ADS. So they can be conserved, but I don't need that.
Then why can't you normalize Cj to be 1?
Yeah, you can.
Oh.
Yeah, it's just that then basically, if you do that, okay, that's another reason you can see phi xxt cannot be 0. Because if you do that, then the right hand side you have 1. So a combination of like there is no way you can have 0 for this 3-point function and something non-zero on the right hand side. You can again show that the energy condition that I showed you earlier, that's still valid even when you have this extra high spin single trace primary operator in your spectrum. And again, you can perform this kind of collider experiment when you are preparing the state using this high spin operator. So as I said earlier, this expression value should be positive, and you can actually show that there are no consistent solutions. So because you can check, you can choose different polarization for this particular operator. If you want to satisfy this for all possible polarization of this operator, there are no solutions. Which basically that means this 3-point function has to vanish. That means this operator x it cannot exist. Okay, so okay. So you can, if you have a finite number of such operators, you can actually run the same argument for all of them. So you can rule out even if you have more than one operator but a finite number of them, it's basically you get the same final result. You can rule all of them out. So the only way one can have high spin single trace primary without violating causality and the chaos bound if you add an infinite tower of high spin single trace primary operators here. That's the only way you can restore causality. But even that's not sufficient. First of all, the OP coefficients of all this entire tower, they should be finely tuned. And second of all, you can show very easily from the safety argument that this at least an infinite subset of all this operator, they should appear in the TP OPE. So what it means is the following. So even if you just consider CFT correlation function where your external operators are either stress tensor or any low spin operator, even then this infinite tau will contribute. That means basically this will give you this will correspond to the new gap that appears, and this will be given by the operator with the lowest dimension. In the gravity language, I can just translate this the last couple of slides in the gravity language. So again, this is a spectrum of high spin particles in ADS. So this is the cutoff scale. This can be spin scale, so there can be an infinite tower of particles of this scale. And you add some finite number of massive high spin particles here. So again, it violates causality, and only way you can save it by actually adding an infinite tower. And now, so before you add this particles, you had Einstein gravity below much below scale lambda. Now you have Einstein gravity below the scale m. Because all these particles, they will contribute to let's say gravitational 4-point function. So it will change your it will so these effects will be visible at the energy scale m. Similar bonds can be derived even in that space by studying iconial scattering. So you have high spin scalar going to high spin scalar, and you are in the limit where the center of mass energy is larger than the transfer energy, and the transfer energy is larger than the mass square of individual particles. For simplicity, let me make this scalar phi. You don't have to make this. This condition is not required, but it makes things a lot simpler. Then only thing that can be exchanged is basically gravitons. And in this iconal limit, you can just compute the tree level amplitude, and you can define something, define this delta in the impact parameter space. Basically, where you are integrating only over the transverse momentum. So this delta is called phase shift, and it has interesting properties. But before that, let me tell you that the tree level diagram is not the only diagram that you should consider. You should also consider all the ladder diagrams. But if you sum over all the ladder diagrams in the iconal limit, they exponentiate. So the full amplitude is given by something like this, right? This is only the tree level result. So whenever that happens, this delta, it satisfies a positivity condition. So when it exponentiates like this, you can relate this delta to something like a Shapiro time delay for the higher spin particles. So that should be positive. So this is something that Kamano, Edelstein, Maldacena, and Zaviadov, they considered in their 2014 paper. And this delta has one more interesting property. So you can just compare this tree level delta. It's given by only the 3-point amplitude between the scalar graviton and higher spin graviton. Not only that, they are on-shell 3-point amplitudes. So they are fixed by Lorentz invariance. So you can just basically this delta, you can just find out the most general structure that you can get just from Lorentz invariance. Then, if you impose this positivity in the regime where you are in the large S regime, as you always do in the iconal limit, but you are looking at a distance scale which is smaller than the mass of individual particles, then you can show that there are no solutions to this positivity condition, that this 3-point function or 3-point amplitude has to vanish. And this contradicts with the equivalence principle that we use for PFT because of Weinberg's paper, 1964 paper, which says that this 3-point function cannot vanish, basically. So, in other words, if you want to have a causal theory after you okay, so what it means is the following: if you give me a theory with higher spin particle, and then if you want to couple that theory to gravity, only way you can preserve causality if you don't have any higher spin particles or a finite number of higher spin particles. And so far, whenever it's so this bound is applicable only for elementary particles. But what I mean by an elementary particle, that's very important, because all I'm doing is effective field theory. So when I say elementary particle, it should be understood from the perspective of effective field theory. as long as a particle looks like elementary particle up to an energy scale which is higher than its mass, this bound is valid for that particle. So a composite particle with mass m which looks elementary up to some cutoff scale which is parametrically higher than m, then this bound is applicable to that particle as well. Also, a composite high spin particle which is isolated enough such that when it interacts with high energy graviton, it doesn't decay into something else. Even for that scenario, our bound is applicable. Okay, I have 3 minutes, so I can just let me just briefly go. Okay, so let me just briefly go over the important points. So all our results, they are either in ADS or in flat space. I don't know of equivalent statement in de Sitter, but generally the point of view that people take is the following. So this is the point of view that this 2014 paper they made the same assumption. And there are other papers which do the same thing. It's basically they just take the ADS or flat space bound and they just assume that that's true even in de Sitter. And it's not a very unreasonable assumption for the following reason. All these bounds are derived using very high energy scattering. And so this high energy scattering is it's not unreasonable to assume that they are insensitive to space-time curvature. So it's not unreasonable that these bounds might be true even in de Sitter. And because of that, they have an application in inflation. So let me because I don't have time, so let me just tell you what kind of things you can constrain. For example, an interaction like this in the bulk. Interactions of this form where W is Weyl tensor, it's easier to constrain them from the CFT side. If you want, you can do the same thing in the gravity side, but generally it's easier to do it from the CFT point of view because there it's very simple. So it's basically it will tell you that all this alpha it should be suppressed by some scale lambda, and this log appears in 4D because of IR divergences. So this amplitude of chiral gravity waves it's proportional to this alpha. So all these causality bounds basically they are telling you this A cannot be very large. This is suppressed by first of all slower parameter and also by this number which is very very small. Similarly, you can also constrain graviton non-Gaussianity, but let me move on to something more interesting. Okay, so let me talk about the effect of higher spin particles during inflation. So there is the mass of higher spin particle has a constraint which goes by the name Higuchi bound. This is more like CFT unitarity bound. The mass of a particle with spin J cannot be smaller than this. So our bound is stronger than the Higuchi bound. So it says that all the mass of higher spin particles they should be larger than the cutoff scale, which is always larger than the Hubble. And in a paper by Cunningham and Maldacena in 2015, they showed that if higher spin particles are present during inflation, they produce distinct signature on the non-Gaussianity of scalar fluctuation in the squeeze limit. So this is what they showed. If you take the 3-point function of scalar curvature perturbation in the squeeze limit where this K3 is K3 is short compared to K1 and K2 and this angle is theta, this admits an expansion in spin. So where this function I is also given in their paper. So basically, if you expand this in Legendre polynomial, so the zeroth order, first order and second order contribution comes from spin 0, spin 1 and spin 2 particles present during inflation, and everything else comes from high spin particles. Then if you impose this causality condition, you can just compute this I, and it's exponentially suppressed for j greater than 2. So that means this 3-point function, this is in that infinite expansion, basically you have only 3 terms. Everything else, they are exponentially suppressed by a gap or by a cutoff scale. Now even then, if you measure this, let's say this I3 or I4 or any one of them, only way you can explain that observation by demanding that the cutoff scale is comparable to the Hubble scale. So only then this I3, I4 or even the higher contributions, they can be large enough to be observed. Not only that, this necessarily requires the presence of not one but an infinite tower of higher spin particles with spin greater than 2 and masses comparable to h. And this is very similar to string theory with string scale comparable to the Hubble scale and a very weak coupling to explain smallness of h over m Planck. So one might interpret this, one might interpret observation of any of these quantities as a signature of a theory which looks very similar to string theory. Okay, let me now conclude. CFTs with large central charge and a sparse spectrum must obey the holographic null energy condition. The HET is the reason why CFTs in this class, irrespective of their microscopic details, admit holographic dual description. Any finite number of massive elementary particles with spin more than 2 cannot interact with graviton in a way that preserves causality, especially when the dynamics of graviton at low energies is governed by the Einstein-Hilbert action. An infinite tower of finely tuned high spin particles can still be consistent with causality. However, they necessarily affect the dynamics of graviton at an energy scale comparable to the mass of the particles. The bounds when applied in de Sitter impose constraints on various inflation